Okay, so welcome everyone to this week's Rencontres. Today we have two speakers. Now we're going to have Michael Green, and then in the afternoon at 2 p.m. we'll have Leonardo Castelli. But for now, we are very happy to have Michael, who is going to give us a talk on a novel expression for an integrated correlator in n=4 super-Mills.
Well, thank you very much for the invitation. When I was invited, I was very much hoping to be in Paris, but circumstances changed and I'm online instead. Anyway, I'm going to be talking about a subject I've been working on recently with other people who I will show you in a minute. I want to apologize. Apparently my sound is a bit muffled, but I hope I'm intelligible. So I think I will begin. I decided to begin by giving the main results because that way you can see where we're heading. So the main result is that I'm going to be talking about correlators in n=4 Yang-Mills, but in particular, I'm going to talk about integrated correlators. So this symbol Gn, which will appear throughout the talk, is an integral of the 4-point correlator of superconformal primaries, O2, integrated with a certain measure, which I'll mention later, over the positions of the correlators. The notation is clear. Tau here is the complex coupling constant, and Bn is a function, which I'm going to be talking about later. It's a ratio of a polynomial, a rational polynomial of order 2n-1, divided by 1 plus t to 2n plus 1. N here is the n of SUN. So for this talk, I'll be talking about supersymmetric, SUN supersymmetric, maximally supersymmetric Yang-Mills. So the main results I'm going to talk about are at the top of the slide, an expression for Gn written as an integral of a lattice sum. It's a very simple looking expression. Of course, a lot is hidden in the expression for B. And this satisfies certain quite interesting conditions, not the least of which is this Laplace equation. So the Laplace equation on Gn relates it to Gn plus 1 and Gn minus 1. In other words, it relates these correlators for theories, for SUN theories, with different ends. And in fact, this equation is sufficient to determine the correlator for all SUNs given the correlator for SU2. So this is a very powerful condition. The Laplacian, of course, is Laplacian on the hyperbolic. It's a hyperbolic Laplacian on tau. So this is an exact expression, meaning it determines the form of this integrated correlator for all values of tau and for all n. So let me begin by...
sorry, Michael, one question here. This is not a large n result. That's what you're saying.
That's right. No, you'll see. I'm going to discuss this. The main part of this talk.
Okay.
Discuss the structure of this for all values of n and all values of tau. So and you'll see that it's got it describes a wide variety of things. So these are my main collaborators, Daniel and Concau, who you may well know, Concau Wen and Daniel Doldoni. And we've written so far 3 papers. I'll be talking about the contents of these first 3 papers. There's a 4th paper coming up quite soon, I hope, which I will mention at the end of this talk. We started working on this. Concau Wen and I started working on this with some other people, in particular with Shai Chestis, Silvio Pufu, and Yifan Wang, and they themselves had set up the formalism, starting with an interesting paper, which is the one by Binder et al. So I will be briefly reviewing this earlier work. And I will mention there's a very recent paper by Eric Permuter and Collier, which is very interesting and is on the same subject. Eric I'm not sure if Eric's in the audience, but he might be. The talk will be based on supersymmetric localization. These correlators I'm talking about are defined in terms of the partition function for the n equals 2 theory, which was originally set up by Pestun many years ago. And the talk will, what we're going to talk about are properties of this integrated correlator, which make certain things very explicit. For example, it's explicitly invariant under modular S-duality, Montan-Olive duality. You can expand it to all orders in perturbation theory for any fixed n, and it indicates where this indicates this expansion is very intriguing, and in particular indicates where it has both planar and non-planar contributions, and it's also got instanton contributions, which I will describe. And furthermore, at large n, it reproduces features of the large n expansion that we know are connected to type 2b string theory holographically. So let me begin with a very brief and elementary survey of supersymmetric localization. Of course, I can't discuss this in much detail, but the basic point is that the n equals 2 star theory, which is a finite n equals 2 theory, has a mass parameter in it, and in the limit in which the mass, this is the mass of the hypermultiplet, and the limit in which the mass goes to 0, it reproduces the, it reduces to the superconformal n equals 4 theory. And that's of course, something which is very well known. And in the original paper by Pestun, this was used as a way of understanding, in his case, Wilson loops, both in the n equals 2 and in the n equals 4 theory. He determined the partition function by supersymmetric localization, and this is the expression that he ended up with, which I will say a little bit more about in the next transparency. But it's basically an integral over the vacuum excitation values on the Coulomb branch of the vector multiplet. So this little a is an n minus 1 dimensional integral. There's a delta function there which sets the sums equal to 0. Without that delta function, it would be un, but for sun, you need that constraint. And then there's a van der Monde determinant. This is a matrix model. There's a van der Monde determinant, there's the classical part, the exponential, the Gaussian part. And then there are two factors corresponding. One, the first factor, which I call the perturbative factor, comes from the one loop determinant in the n equals 2 theory. And in the next transparency, I'll briefly show you that it's expressed in terms of a function called the Barnes G function. And then the last factor is the product of a holomorphic and anti-holomorphic partition function for the instantons called the Nekrasov partition function. This can be expressed in terms of Young diagrams in a rather painful way, given the expressions that Nekrasov had in his initial papers. This has the property that in the n equals 4 theory, which is what I'm going to concentrate on, the partition function trivializes. It's equal to 1 essentially, up to some normalization, and that of course makes it rather uninteresting in its own right. But the point that I'm focus on is that the derivatives of this partition function with respect to the mass have a non-trivial limit, and they in fact give you these correlators that I'm talking about. So let me just say briefly, I'll flash on this transparency, which has more details about the partition function, but I'm really in this talk not going to emphasize these details. It's just to show you that these functions can be evaluated, at least using Mathematica. You can evaluate these functions in great detail. So that partition function, when you write the perturbative part explicitly, is written in terms of these functions called H, but H themselves are bilinears in G, and G is a Barnes D function. So just to show you the function, that's the function. It's a complicated function, and I'm not going to return to it. The last factor, the instanton factor, is even more complicated. It's the, as I said, the Nekrasov partition function, which is a product of a holomorphic and anti-holomorphic part corresponding to instantons and anti-instantons. These factors have Fourier modes, sums over instanton number k. It should say k equals 1 to infinity there, actually. And the coefficient of each instanton was given by Nekrasov in terms of a complicated integral, contour integral, and I haven't specified exactly where the contour goes, and I'm not expecting anyone to be able to read this formula in detail, but I just wanted to show you that there is an explicit formula for the instantons, but it's a very clumsy form. It's a beautiful but clumsy formula. Clumsy in the sense that to actually use it to evaluate the coefficients takes a lot of work, and we did a lot of work in one of our earlier papers with Chester and Pufu and Wang, and we abstracted from many examples. We extracted common features of this partition function for any number of instantons and for any n, and it's that abstraction which is the focus of this talk. So first, let me just indicate how, given the partition function, you get the correlators. So the correlators we're talking about are correlators of O2, where there's a standard representation of O2 as a function of x, and y, where y encodes the SU4 quantum number. So y is a null 6 vector, or SO6 vector. And this is a standard way of expressing the gauge invariant operator O2, which is the superconformal primary in the stress tensor multiplet. The correlator has a 3-part, which will not be of much concern to us, won't be of any concern to us, because it would disappear it's got no dependence on the coupling constant. And the second part can be written as a function called tau n, which is the SUN correlator that I'm going to be talking about, multiplied by a sort of kinematic factor, which one can take out, and which we know the form of, but I'm not going to show you it. And this is all actually a fairly standard way of writing a correlator. The correlator itself is not supersymmetric because it's a function of x, and the superalgebra involves the commutator of two supercharges involves a momentum, which is an x derivative. But the integrated correlator is supersymmetric. And what I'm talking about is based on this paper I mentioned earlier by Binder, Chester, Pufu, and Wang, who considered this correlator, although I've slightly changed the notation. So this is an integral of this 4-point correlator, integrated over the positions, but the positions enter in a form of cross ratios, u and v, and there's a certain measure. And the measure, the correlator I'm going to talk about is a correlator which I've called G1 here, which is where the measure has been specified this in terms of r and theta. So instead of u and v, one transforms to r and theta, defined in this equation, and the measure is then defined in the way by this formula. There is a second correlator which we know a lot about, but which is much more complicated to analyze in detail, which has a different measure, and I'm just not going to talk about it. It's called G2 in this slide, but since I'm not going to talk about it, I'm only going to talk about G1. I will drop the 1 from here on. So,
Michael, may I ask a question?
Yeah.
Sorry. Hi. Do these two supersymmetric integrated correlators preserve different amounts of supersymmetry?
No, they preserve the same amount of supersymmetry, but they,
okay.
Yeah.
Thanks.
Right. So this is the point of this earlier work was to realize that you could write that correlator as a derivative on the log of that partition function in the limit that the mass goes to 0. So you take two derivatives with respect to m and then take a Laplacian with respect to tau on that partition function, on the log of the partition function. And that is in fact the correlator I described earlier. So since we know about the partition function, we have a hope of understanding something about the correlator. G2 is analogously is now 4 derivatives with respect to the mass. And I'm not going to talk about it in this talk. So I'm going to call G1, I'm going to call it G from here onwards. And I'm not going to show in detail the calculations which lead to the results I'm talking about, but let me just simply say that given the properties of the Barnes function and given some expertise in Mathematica, which my young collaborators have much more than I do, one can analyze the perturbative expansion in great detail and for many values of n. And also one can analyze the Nekrasov partition function in detail with some effort. And in the case of the one instanton contribution, it's actually rather easy to analytically write down the result of, write down what the expression is for the one instanton contribution for any values of n. But for the k instanton case, it's very difficult, and we just looked at a very large number of different values of n and values of k. And we found a systematic simplification. Actually, we could prove a simplification that happened in the m goes to 0 limit. The only young tableau that contributed to the partition function were in fact rectangular young tableau where k, for instanton number k equal to p times q, with the rectangles were p times q Young diagrams. Anyway, having done all that work, we end up with this rather simple conjectured expression for Gn. So this is the expression I wrote at the beginning, where, let me say more about it. This expression involves this function Bn, which is as I said, a ratio of a polynomial with rational coefficients of order 2n minus 1 divided by a power of 1 plus t. Now this function has certain interesting properties, and I could say now that, well, let me first point out the obvious. This is obviously invariant under SL2Z, which is a Montagne-Olive duality. And it's, of course, that relates tau at different points in moduli space. So that's a duality that acts on the coupling constant of the theory. And it's holographically related to the S duality of the superstring, of the type 2B superstring in the large n limit. Important properties of Bn are that it satisfies this inversion relation, that Bn of t is 1 over t, Bn of 1 over t. And it also satisfies certain integral relations. So it integrates to a constant, and the integral of Bn divided by the square root of t vanishes. Now these properties were rather mysterious to us, but they came out of the analysis of the that I mentioned earlier, the perturbative and non-perturbative parts of the localized partition function. I should mention now that Eric Perlmutter and Collier wrote a paper last week in which they elucidated these properties in a rather interesting way. So I'm not going to talk about that, but these properties have some sort of mathematical background. Examples. So B2, which is the SC2 case, is a very simple function, and B3 is a bit less simple, and so on. And we managed to extract the general value expression for the function Q. So I've written it here. It looks slightly complicated, but the main point is it's the sum of two of polynomials multiplying two Jacobi polynomials, Pn. So Pn in this expression are Jacobi polynomials, and of course they're multiplied by a rational function of a rational polynomial in T. This encodes, as I said, the perturbative expansion of the partition function. So let me summarize in this transparency some properties of that. So the natural way of presenting it is to expand in G squared n in the 't Hooft style, and that's I've called G squared n divided by 4 pi squared, and with that definition, the expansion for any n starts with the following terms, and I've kept the terms up to a to the 7th. One can go as high as one once, and it's a very simple mathematical calculation to go to very high orders. But this already illustrates some interesting features. For a start, every term in this expansion is a rational multiple of an odd zeta value. So this is perturbation expansion of n equals 4 Yang-Mills, but it's the perturbation expansion for the integrated correlator, which is not the sort of thing that people would normally consider. The perturbation expansion for the correlator without the integral is very complicated, is much more complicated than this. And so, this goes on for any order you wish. And there are certain features, therefore, which are rather interesting to look at. Firstly, at every order, there's an odd zeta value. Now, what I just said was that the unintegrated correlator is very complicated. As most of you know, it's even at one loop, it's written in terms of logs and dilogs, well, polylogs in general, at L loops, it's written in terms of polylogs, and at one loop, I guess, it's written in terms of dilogs, which are complicated functions. But once you integrate, everything is much simpler. And we could, it's possible to see that directly by integrating the Feynman diagrams that contribute up to a certain number of loops. And in fact, certain features are easy to see to all orders. So the integrated perturbation expansion has this very simple structure. Notice that up to 3 loops, up to and including 3 loops, only the planar diagrams contribute. Non-planar effects come in at 4 loops. The 1 over n squared term at 4 loops, and then at 5 loops there's a similar term, and at 6 loops you get a 1 over n to the 4th, which you also get at 7 loops. So there's a sort of systematic way in which the non-planar contributions come in. Finding non-planar contributions in n equals 4 Yang-Mills is, of course, something that's quite interesting, because the systematics of it goes beyond what one can see from the integrability of the planar approximation. These facts are known, so explicit calculations have only been done up to 3 loops, actually. But at 4 loops, there are arguments that say that non-planar contributions should start at 4 loops, and indeed here we see that they do.
Michael, a naive question.
Yes.
Is there nothing to be learned from 3-point functions? So if you only take one ddm or one dd tau, that's trivial.
So take one what?
One derivative with respect to the mass or to the coupling.
No, that is trivial, yes.
That's trivial.
That's trivial. The first term occurs as order mass squared. Just from that's easy to see from the Pestoin partition function. If you expand, it's expanded in powers of the mass. Yeah, but let me just say a word or two about the calculations of the. Oh, sorry, that's coming later, I think. Later I will say more about the integrating over the Feynman diagram. But first, let me point out that this expression for B, which has two terms that have Jacobi polynomials, the Jacobi polynomials satisfy a recurrence relation, which relates them at different values of n, which implies that these B's satisfy this differential recurrence relation, that the second derivative of Tbn is related to Bn plus 1, Bn, and Bn minus 1. And that relation, since Bn comes into the definition of Gn, that immediately implies that Gn itself satisfies the recurrence relation that I mentioned at the beginning, which I've called the Laplace difference equation. So this is the equation Gn satisfies. This is, again, I showed this on the first transparency. This follows from that recurrence relation at the top, and it's very interesting because well, once you know that G1 vanishes, G1 being SU1, everything is determined by G2. That once you know, if you input G2 into that equation, you get the G3 and so forth. You can determine everything iteratively once you know G2.
Michael, one question. The n squared term looks like a discrete version of the second derivative with respect to n, and the n term as the first derivative. Does this mean something?
Say that again.
If I look at your n squared term, what is multiplying is a discrete second derivative with respect to n.
Yes.
And the linear term, a first derivative with respect to n. And I wonder if this combination makes some sense.
Well, it's in the end, in the large n limit, you can replace the discrete differences by differentials, and that tells you what the large n. So in the large n limit, the function satisfies a rather simple looking sort of a Laplace equation. I don't really know the meaning of, but it's a Laplace equation involving the Laplacian on tau and the Laplacian on n.
Okay, I see.
So it's like a three-dimensional Laplacian, but I don't have much intuition or any intuition about that.
That looks like what people call the continual Toda equation in 3 dimensions, which was obtained in the larger limit. Maybe I can ask again at the end.
Okay, very good. Yeah. So now the point at the bottom here, I point out that the solution to this equation can be expressed in terms of non-holomorphic Eisenstein series. I'm actually twisting around our logic. We first noticed that the expressions we had from perturbation theory and the instantrons fit into Eisenstein series, and then we noticed this equation. But so let me just mention non-holomorphic Eisenstein series, since they're at the heart of all this. And the second half of my talk will involve more general Eisenstein series. So let me just remind you that a modular form is transforms under SL2Z with holomorphic weight W and anti-holomorphic weight, which I call W hat. If W hat is minus W, then that's a phase. So there's a U1 transformation induced by the SL2Z in that case. And therefore there's a U1 charge, which I'm calling QU, which is twice the weight. And the operators in the stress tensor multiplet, the multiplet formed by operating with supersymmetry transformations on O2, have non-zero and very specific U1 charges. O2 itself has charge 0. I'll come back to this, I hope, in the latter part of my talk. But for the moment, since we're only talking about O2, we're only talking about the weight 0 case. The weight 0 case means that the modular form is a modular function. And an example of a modular functions are these Eisenstein series, defined as double sums over M and N. It's very useful to know that that double sum can be written as in a standard way as an integral over parameter t. So that's where this exponential came in my previous transparencies, e to the minus pi t m plus n tau squared over tau 2. And if you multiply that by t to the n minus 1, then you just reproduce the integral over t reproduces the Eisenstein series. Now the Eisenstein series has a nice Fourier expansion where the Fourier modes, if I go, can you see you can see my cursor, can you, if I do this? Somebody?
Yes.
Yes.
By the way, if my internet cuts out, I will not know that I'm not being listened to. Let's hope it doesn't. The zero mode has two perturbative terms, one of which goes like tau 2 to the s, and the other goes like tau 2 to the 1 minus s. Now, since tau 2 is related to g squared, these are terms which the first one goes like an inverse power of g squared to the s, and the second one goes like a positive power, well, like a power of g squared to the s minus 1. That's the zero mode, and then the non-zero modes contain the instantons, and they are given by they have the phase factor e to the 2 pi I k tau 1, and then they are basically they're basically given by a Bessel function, a k Bessel function, with some coefficient involving a divisor sum. And the Bessel function has the property that at large tau 2, at weak coupling, it decays exponentially in a way which is commensurate with the phase. In other words, it's a characteristic decay for a BPF, a supersymmetric protected instanton. These Eisenstein series satisfy the Laplace eigenvalue equation, which is of course important for what follows. So these are the Eisenstein series are solutions of this Laplace eigenvalue equation, where the eigenvalue is s times s minus 1 in my conventions. So from this integral representation with a t to the s minus 1, you can see that if I change t to the s minus 1 to b of t, I will get the representation I had earlier, the integral representation. So I can see that if I expand b in powers of t, then each power of t will be will give me an Eisenstein series in my expression for the correlator. So that correlator, which was an integral of b times the exponential, can in fact be represented as an infinite sum of Eisenstein series, and b, as I said earlier, b satisfies this inversion relation, which was something we noticed, which was crucial for what follows, but we didn't really understand. But Collier and Perlmutter have some understanding of that from a rather straightforward, actually, observation about expanding in the basis of Eisenstein series. Examples of this for SU2, C2 is just this simple function, and so on. Now the point about this inversion symmetry is it ensures the following: that the infinite sum of Eisenstein series, if you pick out the zero Fourier mode of that infinite sum, involves an infinite sum of terms which are tau 2 to the 1 minus s, which are perfectly fine in perturbation theory, but it also involves an infinite sum of powers of tau 2 to the s, which are inverse powers of g2. But that sum can be resummed using it can be Borel resummed, and it turns out that the infinite sum over positive powers of tau 2 is actually the same, gives the same result as the infinite sum over negative powers of tau 2. And that's what's ensured by this inversion symmetry. And that's what's needed in order to make contact with the perturbative expansion. So the perturbative expansion involves a sum over both positive and negative powers of G2, but the negative powers, of course, diverge term by term at small g. Well, they diverge in a way, but it's diverge in a way that's Borel summable. The instanton contributions you can read off from the non-zero modes of the Eisenstein series, and they can be summed, and each instanton is multiplied by an infinite series if you expand at small y. At small coupling. Here in this expression, y is essentially the inverse coupling squared. So if you expand at large y, which is small coupling, you get the expression at the bottom. But there is an exact expression involving the complementary error function that I've written above that. So one can exactly extract any number of instantons. The one instanton case, of course, is simple. The k instanton case is not so simple, but it can be analyzed for any instanton number by using this formula, which I've extracted from the definition of Gn in terms of in the expression I had at the beginning. In terms of,
sorry, Michael, one question. Is the Eisenstein series expansion asymptotic?
So the Eisenstein series, I should have stressed that. The Eisenstein series is not in any sense convergent. Actually, it's very difficult since the Eisenstein series behave in a rather peculiar way. It's not obviously convergent, but the matrix model expression I wrote down that you get by using the representation for the Eisenstein series as an integral, like the Schwinger-like representation on the previous transparency, is perfectly convergent everywhere. And furthermore, yeah, as far as, yeah.
Okay, thank you.
So now I guess this should have come earlier. This is now a comment about integrating the perturbative contributions, which I mentioned earlier. So let me flash through this. It's not particularly informative. It's just to show you how it works, roughly speaking. We want to integrate over the cross ratios U and V. You parameterize them in some standard way in terms of a triangle, but the sides of a triangle, one on R, and then R cosine theta. And that integration with a suitable redefinition of the measure leads to the following: that the unintegrated correlator, choosing a conformal frame in which one particle has been taken off to infinity, one operator has been taken to infinity. It looks like a ladder diagram, and then when you integrate over the measure, that looks like a two-point function. And these, I haven't enough details to demonstrate that, but there were papers written many years ago on evaluating such diagrams, and the coefficients that I mentioned earlier, which were zeta values, come out of those calculations. So I seem to have something has gone wrong, because I shouldn't have had this transparency here. And sorry, this is a summary of the talk. So I don't know how that transparency got there. So let me continue. So I've talked so far about finite n, about the perturbative and the instanton contributions at finite n. Now let's talk about the large n limit, the expansion in powers of 1 over n. And that can be organized in 't Hooft's way if you, as a genus expansion in powers of n, in powers of n squared, 1 over n squared, and the coefficients which have g with a superscript little g are the coefficients which are functions of the 't Hooft coupling at any genus. So one can analyze this from the equations that I showed earlier up to any genus you wish. at genus 0, which is the lowest, which would correspond to a sum of planar diagrams, the expression that you get from the localization argument is given here. Now here it's given as a power series in lambda. So this is the small lambda expansion. So this is large n and small lambda. So it's like taking the large n limit of the expansion I had earlier, which was the perturbative expansion. But this doesn't, but this is at very small couplings because the radius of convergence is lambda less than pi squared. So this is a convergent expansion. You can express it as a Borel sum, which in terms of the hypergeometric functions, this is the expression. And once you've done that, you can expand this at large lambda. And what you find then is a large lambda expansion, which has this form. However, at large lambda, this is not convergent. So this is the expansion in powers of 1 over lambda, but it isn't Borel summable, which means that there are non-perturbative terms coming in, which I'll mention in a second. But this expression here is the expression that one would get by looking at large n and large lambda. And this expression, in fact, coincides with expressions that were found earlier, in particular by Binder et al. So that first paper I mentioned by Binder, Chester, Kufu, and Wang found this expression, or at least up to some order in 1 over lambda, found this expression.
Sorry, Michael, but what kind of non-perturbative effects do you expect in the large lambda expansion?
Well, I've gotten, you asked the question just as I flipped.
Okay, sorry.
So one can argue that these are, using resurgence, that these are terms of this form involving exponentials of -2 root lambda. Now, why these come in, we're not quite sure because it's not completely obvious. These have the form of instantonic, world-treat instanton contributions, but they're presumably due to the fact that when you do a functional integral over the world-treat in the holographically, in the dual string theory, the world-treat is pinned at 4 points on the boundary where the operators are, it ought to give rise to such an instanton. We haven't pursued that and we haven't understood it, but that is, this rather precise expression is what emerges from this analysis. I should say that similar expressions arise in other contexts. For example, in the calculation of the Cuspallon dimension, there is a similar but rather power of root, an exponential of minus, I think in that case it's -1/2 root lambda. And then this is the planar diagrams. One can go further, and in our paper we went to the next order. So this is a Tooth expansion in which lambda is large, this second point. Rather more interesting, perhaps, is to do the large n expansion with a fixed coupling constant instead of fixing lambda. With fixed lambda, of course, I should have emphasized the large n limit kills the instanton contributions. The instanton contributions are suppressed by powers of e to the -n. The instanton contributions, of course, are crucial for understanding how SL2Z, how Montanaro-Olive duality works. So if you keep G squared fixed, then S duality can be manifest. So, and in that case, there's some rather interesting comparisons with string theory in type 2B string theory in ADS5 cross S5. So one can understand the large n expansion of this function Bn. In fact, the best way of understanding it is to see how the differential recurrence relation that Bn satisfies works at large n. And then this is the summary of what one finds. So we're talking about the large n expansion with fixed tau, tau being the coupling constant, the complex coupling constant. The first few terms in this series were understood in the older papers that we had with Kufu and Wang and Chester. But given our the differential recurrence relation, or the Laplace difference equation, in fact determines all the coefficients from a smaller set. It doesn't actually fix all the coefficients uniquely, but given, for example, given you'll see that the Eisenstein series E3 halves occurs at order n to the half. It also occurs at order n to the minus 3 halves. So it's 1 over n squared suppressed. And there's an infinite chain of recurrences at order 1 over n in a 1 over n squared series. So, and given the first Eisenstein series E3 halves, all the other ones are determined by using that difference equation, the Laplace difference equation. And there's a lot of that Laplace difference equation has a lot of power in determining coefficients. But anyway, this series is a power series in half integer powers of n, apart from the very first term. The first term being the dual to the supergravity and type 2b supergravity in 10 dimensions. The term of order n to the half. Let me just the term of order n to the half is the term which is connected via holography to string theory to the r to the fourth coefficient in string theory, and the term of order d to the fourth r to the fourth, the Eisenstein series E5 halves, is closely connected to the d to the fourth r to the fourth term. So those are the BPS terms which are understood within string theory. This, of course, involves an infinite number of further terms, but it's not at all clear beyond the term I mentioned how these are connected to the amplitudes of string theory directly. I mean, when I say string theory, I'm saying that if you take the flat space limit, take large n limit and the flat space limit in a way which has become fairly standard now, then you can pick out these three terms. But there are terms missing, of course. So this integrated correlator doesn't, the integration washes out some of the structure. So it's obviously not as detailed as understanding the correlator, the unintegrated correlator. And in particular, you can see then there's no term of order 1 over n. The term of 1 over n corresponds to a d to the 6th r to the 4th term. And that term, we understand how it arises from the second correlator, the correlator I haven't been talking about, to the d to the 4th, to the dm to the 4th correlator.
Sorry, Michael. Is there any reason to expect that the 1 over n expansion should be related to the derivative expansion?
Is there any reason to expect it? Yes, in this limit. In this limit, where g is fixed, then it counts what the 1 over n, the powers of 1 over n count the number of derivatives. So n squared, of course, is the Einstein-Hilbert contribution, which is of order 1 over alpha prime to the 4th in my notation. If you take 3 derivatives, you get a term of order r to the 4th, sorry, six derivatives, which is 3 powers of alpha prime. So that next term is order 1 over alpha prime, and that translates, just using the usual holographic translation, to a term of order n to the half. And then the next term in this expression is powers of alpha prime higher.
Okay, yeah, I see the logic.
Right.
Thank you.
But what is missing, of course, there are infinite numbers of terms missing. The terms of order 1 over n and integer powers of 1 over n. And in particular, the term of order d to the 6th r to the 4th. Furthermore, the coefficients in front, of r to the 4th should match and does match precisely with what one expects in string theory, the term of order d to the fourth out of the fourth, that's what it looks like. It looks like d to the fourth out of the fourth in flat space, but actually, of course, we're on ADS, so it's really a compactified version of d to the fourth out of the fourth, and that picks up contributions which are not simply d to the fourth out of the fourth, but which are in flat space, but also the terms which are really corrections to the out of the fourth term, because of the compactification. The derivative, if it points in the on the 5 sphere, will be replaced by a constant. So you can't make a one-to-one correspondence between the coefficients in this expansion and the flat space results. You need more information, and that extra information, in fact, comes from the second correlator. So the second correlator, which contains terms which are powers of both powers of half integer powers of n and integer powers, that gives more information, and that permits a comparison of the d to the fourth out of the fourth coefficient with the flat space result. Now but otherwise the higher order terms are very difficult to make any connection with terms in string theory. It's just with the coefficients of terms in string theory.
Michael? Yeah, in particular, I mean, even combining both integrated correlators, we don't have enough information to nail down, say, d to the 8th or to the 4th. I mean, we can't undo the integral in any way that tells us what we really want to know, right?
No, that's certainly true, and it's also, but even at d to the 6th out of the 4th, you need 3 pieces of information, so you need 2 pieces of information for d to the 4th out of the 4th, and those are given by the 2 correlators I mentioned. D to the 6th out of the 4th, you don't have enough information even then, just from the correlators, to determine the coefficients. You need to input something more from flat space, from the string theory in flat space. Anyway, so that's where I've got to. I think I'm going to. I had intended to talk about a slight expansion of this subject, but I see time is going to run out. Let me just say what it was that I was going to talk about. There's another piece of work that we did, which generalized from these 4-point correlators to n-point correlators of a very special type. There's a U1 charge that, as I mentioned, carried by the members of the stress tensor multiplet. So this is the stress tensor multiplet, and if you go down, follow the red arrows down to the left, I'm going from the top state to the states which are related by one kind of supersymmetry. Half the supersymmetry take you down to the left. So, for example, three steps take you to the operator called lambda, which is dual to the Dilichino in the holographic map, and is basically the trace of the Yang-Mills, the self-dual Yang-Mills F times a fermion little lambda. That's shown here. And the next one, the O, what I call O tau, is the operator which is 4 steps down. This is the chiral Lagrangian. So these operators carry U1 charge, and one can look at special correlators which violate this U1 charge. Maybe I'll just show the rest of this transparency. This U1 charge in the Yang-Mills was discussed a long time ago by an intriligator who called it the bonus U1 charge, or bonus U1 symmetry, and it's broken. There's a pattern of its breaking, so that it's conserved. The U1 charge is conserved by all the 4-point correlators. So the correlator I just talked about is one of these 4-point correlators, but they all conserve the U1. But more interestingly, n-point correlators violate the U1 by at most 2n minus 8 units, the U1 charge, and so there's a set of maximal U1 violating correlators, which violate the U1 by precisely 2n minus 8 units. And we generalized the discussion of the 4-point correlator to include arbitrary U1 charge violation but I don't have time to talk about it. It's on the next topic.
Actually, you still have quite a bit of time, Michael. So usually we do 1 hour talk with 15 minutes for questions. But so.
Well, I'll flash through these transparencies, which may not be all that informative. But so basically, the idea is to use the structure that I talked about for the 4-point correlator, but to extend it. So this gives just examples of what I'm talking about. This lambda operator, this composite operator dual to the Delitino, there's a 16-point correlator, 16 of these lambdas, which violate the U1 charge by 24 units. Each lambda has 3 halves, charge 3 halves, and when you've got 16 of them, that's 24 units. Remember that the charge was twice the weight, the modular weight. So these, I should have said that before. These operators transform with weight, with holomorphic and anti-holomorphic weights, W and minus W. And in the case of lambda, W is 3/4, so their charge is 3 halves. In the case of the chiral Lagrangian, the weight is 1, and so the charge is 2. The charge being W minus W prime, where W prime is the anti-holomorphic weight. So the 16-point lambda correlator violates the U1 charge by 12 units because there are 16 lambdas. This class of correlators where you have 4 O2s and then any number, little m, of O taus, of chiral Lagrangians, well, that violates the charge by 2W, which is 2m. So in that case, the holomorphic weight is m, because each O transforms with weight 1. Now, you could actually construct this latter one, any correlator of this form, you can construct by acting on the 4-point correlator with certain derivatives, and these are modular covariant derivatives. So this is the definition that we're taking of the covariant derivative, which is a derivative which changes the weights acting on a modular form of weight W minus W. It changes it to a form of weight W plus 1 and minus W minus 1. It increases W by 1. And then there's a conjugate D bar, which decreases the weight by 1. But the point is, acting on the integral, on the integrated correlator, I'm sorry, I said that wrong, acting on any correlator. So this is what I'm saying now has nothing to do with the fact that the correlators are integrated. Take a correlator, act with D on it, and it brings down from the action, the exponential of the action occurs inside the definition of the correlator. And when you act with D, it brings down 1 power of O tau integrated over the position. Oops. So you can make this weight W correlator by acting successively with covariant derivatives. The covariant derivatives have a weight, an index W, which indicates the weight of the operator that they're acting on. So the first one acts on, we're acting on a 4-point correlator which has weight 0, and then we act successively with W factors of D, and that generates the correlator. And then we can simply expand it in perturbation theory. Since we know the correlator from our previous, from the previous work, we can see what the correlators look like for any weight. So these are the correlators for any weight. There's a silly subscript 0 here. The 0 simply means it's the 0 Fourier mode, which means it's the perturbative part. So these are the perturbative parts of the correlators. And you see that they all begin with, well, the weight W correlators begin at order G squared to the W. And that's something which is clear when you write the, if you write the correlator, the Feynman diagrams which contribute to these correlators, you'll see that again, of course, this checks with what one expects.
No.
What? Hello?
You can continue.
Did something happen?
Let's hope not.
This is the expression, so you can extract the general expression. So for these correlators in perturbation expansion. And then you can look at the instantons, and the instantons have, now in these cases, the instantons and the anti-instantons are different. In the earlier case, the correlator was a real function which had equal contributions from instantons and anti-instantons. But here, the anti-instantons are suppressed relative to the instantons by powers of 1 over tau2, tau2 being 1 over the coupling constant. And these factors, I haven't got time to show it, but these factors are actually what you would expect by if you did semi-classical instanton calculations. These come from fermionic zero modes, needless to say, they correspond to what one expects. Right. So now I had a summary transparency, but for some reason that I don't understand, it got inserted here. This just summarizes what I've said, basically, that in the first point is that we've looked at these correlators, and we looked at the maximal U1 violating one. I didn't say much about the second correlator, but we wrote a paper with these people on it. We looked at the large N expansion, and there we find that instead of being a sum of Eisenstein series, remember the large N expansion was a power series with half integer powers of n, where the coefficients were Eisenstein series. Now the 1 over n. Now we have integer powers of 1 over n, and for the integer powers of 1 over n, the coefficients are what we call generalized Eisenstein series, which are of the type that many years ago I and Pierre Van Hove saw describe the d to the 6th after the 4th term. So they satisfy Laplace eigenvalue equations, but with right-hand sides which are quadratic in Eisenstein series. So these are rather fascinating equations. They satisfy rather fascinating equations, and they are the coefficients in the 1 over n expansion for this second correlator for the integer powers of 1 over n. And I've just made some vague statements about how this large N expansion has something to do with scattering amplitudes in ADS 5 plus S5, but since we're integrating over the correlators, we're losing information. And in order to recover some of that information, you need to have more data, more correlators. And that's the summary of my talk. I added a transparency about something which is not yet in the literature, that we haven't yet put out. But let me just say that we've been looking at the generalization of everything I've talked about from SUN to SON and USPN. And that, of course, is a somewhat richer system because it involves duality of a richer duality, which is related to Langland's duality. It involves Goddard-Neutz-Olive transformations, which relate SUN. SUN and SO2n are self-dual, but SO2n plus 1 is related to USP2n and vice versa by this duality. So we've understood how that works within the framework that I've been talking about, but I haven't had any time to talk about it, and furthermore, it's not yet published, so I don't want to talk about it in detail. So finally, let me just say I'm very happy to have this opportunity to talk. It's a pity I'm looking at a flat screen instead of the beautiful streets of Paris, but I thank you anyway.
All right, let's thank the speaker. Okay, so questions?
I may have one. Hi, Michael. So when you wrote the large N expansion of your G1 function, all the Eisenstein series that show up seems to be exactly the same that appear in the low energy expansion of the one loop correction in 11-dimensional supergravity amplitude that you use also to relate to the type 2B. And what you propose for what you wrote very briefly for G2 seems to correspond to the two loop. Is that true? And is there any reason for that?
there is some sort of correspondence. Are you talking about taking 11-dimensional supergravity on a torus? Is that?
Yeah, I'm talking about 11-dimensional supergravity on T2. Yeah.
Yes. So it is the same sort of functions come in. Yes, but they don't. I've not been able to understand any detailed connection other than the statement that that's where these functions that satisfy this generalized Laplace equation come in. They come in from, you get them in, there are two loops on a torus, and you get Eisenstein series from one loop on a torus. But
and exactly the same, right? Because you get 3 half, 5 half, and all the integer increment exactly as you have in your large N expansion.
So when you say exactly the same, you don't mean the coefficients are the same.
The coefficients are not the same. I'm just saying that the S value are exactly the same.
Yeah. Yes. So one of the intriguing features which I didn't emphasize, that I should have emphasized, is that the S values, of course, for the Eisenstein case, for the case I talked about most, the first correlator, in the large N expansion, the Eisenstein series that appeared were half-integer index Eisenstein series. But in the finite N case, where I wrote the correlator as an infinite sum of Eisenstein series, those were integer index Eisenstein series. So in going from finite N to large N, there's a changeover from integer S Eisenstein series to half integer S Eisenstein series, and correspondingly, as I think is understood by in other contexts, there's a change in perturbation theory from even powers of G squared N when you are at finite N. So standard perturbation theory done by Tuft at finite N is a series of in powers of G squared N, whilst in the large N limit with the large Tuft coupling lambda, it's a series of inverse powers of lambda to the half integer powers of lambda. So there's a changeover which is manifest in our expression, but it's not obvious why that happens.
Well, I think from the point of view of enforcing SL2Z invariance, you can derive that generally.
Right.
So actually, if you look at some more complicated observable than these integrated correlators in, say, N equals 4 super Yang-Mills that obeys S-duality invariance, then it will have that structure. Not necessarily that it's just Eisenstein's, but say it's in the strong coupling large N limit, the Eisenstein pieces that appear will have half integer indices. So the changeover from integer to half integer is something you can derive in general as a consequence of S-duality. There may, of course, just like for this other integrated correlator, be more complicated functions appearing than just the Eisensteins, but the
Sorry, what do you mean by
S-duality
S-duality?
power expansion. I mean SL2Z invariance of the...
Yeah, but any Eisenstein series for any value of S or any cuspidal form is SL2Z invariant, so I don't see how you could get clues on the value of S by S-duality. This is what I don't understand.
So the other piece of information is that you input that the object you're studying has a well-defined perturbative expansion. So you're using physics to say, I'm studying an object
to get
in
the
N equals
power
4. In perturbation theory, it's integer powers of G squared. What does this imply? And it implies what I said. So that's the extra piece of information. So if you like the integer series in weak coupling perturbation theory is an input, the output is the half integer series at strong coupling.
Okay, fine.
Risha, go ahead.
I have two questions. So the first question, so your final expression for the integrated correlator, just linear combination of the Stein series, if you just look at it, it's just given by the perturbative part at V coupling, plus instanton plus anti-instantons. Right?
Yeah.
But there is no instanton, anti-instanton contribution there, it looks like.
Not in that correlator. In the other correlator. There is in the other correlator, which is more complicated. There is even, well, in the zero mode, there are perturbative terms, but also anti-instanton terms.
That's the hindsight. If I start from localization prediction, when you have integral or matrix model integral, there you have partition function modulo square.
Yes.
For instantons. Therefore, naively, if I will expand it in powers of the instanton modes, you do expect to have instanton, anti-instanton, and inference terms.
Yes.
My question is, what happens? As a miracle disappear or what?
No, well, I don't think it's a miracle because I don't believe in miracles. But I think the point is that the first of these correlators is rather elementary in the sense that we're expanding in powers of m and then setting m equal to 0. So the first correlator involved the second derivative with respect to m, and I don't really understand why, but there are no instanton anti-instanton pairs in the m squared part of the partition function, or of the log of the partition function. But when we do 4 derivatives with respect to m, which is the second correlator, then indeed we pick up instanton anti-instanton pairs. And they're probably there for reasons that you just said. They're probably generic to that partition function.
And second question, you mentioned some moment that you have this non-predictive it Hooft limit for large planar limit and lambda to infinity. You have non-predictive scales appearing in the expansion of large lambda.
Yeah.
And which kind of similar to what one gets for the Caspar anomalous dimension. For the Caspar anomalous dimension, somehow we understand that it's related to very special limit for correlation function, in the sense that it's related to the limit when, from point of view of point correlation function, when you have some light-like distances, or another way in the OP expansion, you have contribution of operator with large spin. So now you have an integrated correlation function. So does it mean that somehow secretly in this integral of for point correlation functions, there is some important contribution coming from the operator with large spin? Or another way, could you say, in a certain sense, could you say that which operators from point of view of the OP dominate integrated for point correlation function?
In that limit?
Whatever, I mean, yeah, at least in this limit, lambda to infinity, yes.
In the large n and large n.
Yeah.
Oh, that's an interesting point, but I don't know the answer to that. But it's a good question. Okay.
Thank you.
Yeah, so let me just add to that. So no one has considered given that you know the result for the integrated result, just seeing what this means as some rule on the CFT data by expanding the correlator into conformal blocks or something like this. No one has done this.
To my knowledge, no one has, although that is indeed an obvious thing to do.
There's also some numerical predictions for this correlator from the bootstrap, I believe.
Yes, yeah. I don't think anyone has done that, at least systematically. But it is, yeah, it's an obvious good thing to do.
Himanshu Raj, postdoc here at Sakle, and I were looking at this, mainly Himanshu. It seems actually very preliminarily, it seems that you will not get the ideal sum rule, that is to say, a positive sum rule. And so it seems hard to actually extract individual information about OPE coefficients because you have signs, and there's also some divergences in the problem that at large delta, which Shai et al. Found in their recent paper. So I'm not sure what that would look like, but it actually seems maybe not promising at first.
I see.
Some extra linear constraint that you can add to the numerics, for instance. It's more like this, even if it's not positive, it's just some extra equation.
Yeah, I think it would be nice to derive it and stare at it and use it, but yeah, it seems a bit tricky.
More questions?
I have a question. Now, with M non-zero, you have a non-trivial theory that flows to n equal 2 star in the infrared. And if I remember correctly, the infrared theory is non-trivial. So can one get similar types of integrated information for the infrared theory?
That's another question I don't know the answer to. I mean, it will be much more complicated.
Is the limit m to infinity of the localization result known or understood?
I thought. Well, isn't that the n equals 2 theory?
Right.
What do you mean? Is it understood?
I mean, whether it's something that's tractable.
Oh. I can't remember. Was that discussed by Pestun in his paper?
I don't know.
No. No, the problem is that it's a non-conformal.
Right.
And the Pestun localization story was basically on the sphere. So if you have something non-conformal on the sphere and something non-conformal in the plate space, it's different stories.
Right.
Well, it's non-conformal, but you can still get an integrated correlator. And if I remember correctly, the SL2 symmetry is valid over the whole line, right?
No. Well, n equal 2 is not self-dual.
Sorry. So the operators.
The question is, do you expect SL2 series, n equal to series to have SL2Z invariant?
Well, it depends. If the operators, I don't know how the operators transform at the SL2Z. If they transform.
No, it's Zyberg-Witten. N equal 2 will transform into magnetic series in the SL2Z transformations.
So you're saying then that the SL2 invariance is an artifact of the M to 0 limit? That is, and the question is, at what point is it supposed to be broken?
No, I'm saying that if you start with an N equal 4 series, N equal 4 series, it goes into itself out and the electromagnetic duality. You introduce M, so you automatically break in supersymmetry down to N equal 2, and then you don't have this argument that series of
right, but then I would have expected that the expansion around M equal to 0, eventually the terms will be non-invariant, right?
Indeed. But then,
is this what people see?
Yeah, but then what Michael was discussing, there are two special operators, which on one hand said you're right, that expansion around M equal to 0, you don't expect him to have the 2Z invariance random terms of the expansion, but there is these two special operators which somehow preserve this 2Z invariance.
I see. So this is only special for these two, but the rest terms of the expansion are not.
We don't know.
I see.
I don't know what's known about that. Is that if you expand to some finite order in M beyond 4, I would have thought that would also be SO, and take the limit M goes to 0. But to any finite order, the terms will be SO2Z invariant.
That contradicts what Grisha said.
Well, that's why I'm questioning. I actually don't know, but.
Well, do the operators transform under SL2Z, the operators you're perturbing with?
So yeah, it seems like it has to be SL2Z invariant because each derivative brings down an integrated operator in the stress tensor multiplet. This is a half BPS operator. It's trivially SL2Z
That's what I would have thought.
Correlator will be.
Yeah, that was why I thought it would be true. But in the M goes to 0 limit.
Right, we do that so that we write this as an integrated correlator in the UV theory, and then we get to use everything we've been saying. And
if this is correct, then if there is any breaking of SL2Z, it has to be non-perturbative in M. Which could be, I don't know.
Any more questions?
I wanted to ask if you were willing to hazard a guess about the structure of the unintegrated correlator beyond the 4 loops where it's been explicitly computed. So, you know, whether as regards the transcendentality structure of the coefficients or the order of the non-planar corrections, do you feel that
I thought the non-planar
this is helpful there?
I thought there was a fairly well understood argument. But beyond 4 loops, 4 loops and beyond, you get non-planar correction. I mean,
and do you think that would they all appear in the integrated correlator to all orders, and then vice versa? Do the coefficients of the integrated correlator? I mean, they seem to just be these single zetas, but for the unintegrated one, do you have a guess for what those coefficients might look like?
No. Well, I mean, they involve they're horrible functions of the cross ratios, right?
Right.
And you want me to guess what the arbitrary loop correlator looks like?
Well, maybe just some systematics of it. I'm just trying to ask aloud, the question that is lurking behind all of these observables where we're integrating something. Can we learn something about the unintegrated thing? I mean, what this requires some inspired guesswork.
There are certainly experts on this screen in front of me who have more chance of making inspired guesses for that.
Sorry, go ahead.
You mentioned about the second. What's actually known about the second integrated correlator? So you mentioned that you're expecting to have interference terms instant on anti-instant term.
Yeah.
At least at coupling. But what else is known about this fourth integrated correlator? The second integrated correlator.
Well, as I said, the coefficient in the large N limit, in large N expansion, the coefficients involve sums of these functions that satisfy this Laplace eigenvalue equation with a source term that's quadratic in Eisenstein series. So that equation for each of these coefficients has been analyzed in some detail, and so each of those functions has a certain number of the zero mode has a certain number of perturbative terms, power behaved terms, and a contribution from an infinite sum of instanton anti-instanton pairs. That's in the zero mode. The non-zero mode, of course, in other words, the modes in which the contributions which have non-zero instanton number are extensions of that. I mean, it's quite complicated to say what it is, but basically, it's the non-zero modes have instantons plus instanton anti-instanton pairs. So, I mean, one particular function of that type has been analyzed a great deal, which is the function that occurs in string theory. So it's a function of order d to the sixth r to the fourth in the notation I was using. It's a term of order 1 over n. The first example of one of these functions comes in at order 1 over n, and that satisfies a Laplace equation of the form Laplacian minus 12 acting on this function is equal to the square of E3 of the Eisenstein series E3 halves. And what I and Pierre originally looked at, and then we analyzed in great detail that solution. It's got 4, instead of having 2 power behaved terms in the zero mode, it's got 4 power behaved terms, which in string theory contribute to tree level up to genus 3. But it also has, as I said, an instanton anti-instanton pairs. So, but beyond that, well, I mean, there's a certain amount more is known, but.
Thank you.
Does it obey a generalized Laplace difference equation?
Does it obey a generalized Laplace difference equation? That's a good question, which I don't know the answer to.
I suggest we wrap up, at least to close the YouTube recording, and then we can keep discussing afterwards. So let's thank Michael again for a very nice talk.